Hello and welcome back to, I think this would be the last video on gradient descent tutorial part 4. My name is Chieh from Northeastern University. So from the last video, we kind of did an example of the best fit line, right? And where here's the data, and using gradient descent, we can essentially find this line, this line right here that gives you the best fit. In other words, we found the alpha and beta of the line. And you may have remembered the actual result was zero 0.5 and zero 0.5. And the result we got was 0.49, 0.5. So it was pretty close. And if you plot out the results over time, it little by little converges. Like these are all the previous lines, and eventually it converges towards like the optimal line. Now with gradient descent, if you remember, we end up having this formula where this right here is the derivative, and over here is the guess, initial guess. Now this summation is depends on the number of data, right? You have right here we have 4 data, like as you can see, x1 to x4, and therefore we only need to sum up 4 times. And even with 4 times, you can see that this gets really, really big. Now, what happens if you, instead of 4, you have 100, maybe 1,000, a billion, 1 billion? Can you imagine how long this would be? This would be like super, super long. And there'll be a lot of calculation. So we came up, oh, not we, but there's another way to do gradient descent that even with very large data, you can converge, and you can actually converge to the right value much faster than gradient descent. And this approach is called stochastic gradient descent, right? This actually does much better. What it says is that stochastic gradient descent is that you just assume for the first run, right? So you start with alpha 0, beta 0. And to get alpha 1, beta 1, all you have to do is just pick the first data, the first one. Okay? So you don't need the sum anymore because you're only looking at the very first data. Well, actually, let me rephrase that. You don't want to do the first data. You want to randomize. Randomize. All right. So let's say you shuffle your data. So these are completely random where they go. Once you have shuffled the data, then you can pick the first one. First one. So you pick the first one, right? And then you just solve gradient descent. And then you pick the second one. Now, you see this is x1, 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 y1. Now you pick x2, and you solve gradient descent. And then you do x3, x4, so on and so forth. So you, instead of needing to sum up all of them, just do them one at a time. And once you've gone through every single one of the data, like once you've gone through all of them, start with the first one again. And then start on the second one again. So once you go through, once again. And eventually, it will converge so that the new alpha and the new one and the old one are basically the same. That the alpha and the beta are no longer changing. And that's it. That's stochastic gradient descent. And believe it or not, this is much, much faster at converging. Let me show you. So this right here, notice they're only like 1, 2, 3. There are only 3 gray lines here. So it converged very, very fast. And the speed was much faster. So the actual result was this. And gradient from stochastic gradient descent, it's a little bit off, but the result is still pretty good. It's a bigger error, but like notice it's significantly fewer lines. Like let's look at them side by side, right? Side by side comparison. Look at how quickly it converts to the right solution versus this. This took quite a while. It like jumped from here to here to here to here to here and eventually reached this. Whereas this one, it just went right in. So stochastic gradient descent does like much faster. Yeah, it was slightly off, but for a lot of applications, this is good enough. This is good enough. I mean, look at this. Look at, oops, look at this versus this. It's basically the same. I mean, it's not that far off. So I guess it depends on the some application. Certain ones might be more important that you really, really need it to be accurate. Other ones, maybe good enough is good enough. So, of course, people came up with a compromise. So this is the regular gradient descent, also called a batch gradient descent, and this is the stochastic gradient descent. And there's a compromise. Well, batch gradient descent uses all the samples. Stochastic gradient descent uses only one sample. So why don't we just use something in between, like called a mini batch gradient descent? So we don't use one or we don't use all of them. We use some n sample that is greater than one, but it's less than m. So you pick something that's reasonable and you do it from there. And it turns out the mini batch gradient descent, um, I think it converges even faster than the stochastic gradient descent. So yeah, this is a technique of gradient descent, which is very, very useful in all sorts of aspects of life. If you ever want to do like machine learning or optimization kind of things. So I think that's it. I hope it made sense, and thank you for watching.